Okay, so now we are really getting to the good stuff. And I have not a whole lot of time left, so I want to make sure that we get this done. Okay, so problem 10 says to write the Verilog code for the JKT and SR flip-flops as described in homework 0B. And then write the code corresponding to the characteristic equation and a different one corresponding to the state diagram or characteristic table. Now I'm going to look and see what you need to use in problem 11. Make sure that we do our example. So problem 11 that you have to turn in is create a one flip-flop circuit as described, 2 Verilog codes, one based on characteristic equation, one based on the characteristic table. Okay, so you'll follow very similar steps to what we're going to do here to get what you would get for yours. So I will do JK, since JK has 2 inputs and yours has 2 inputs. So the first thing I'm going to want to do is to think about what a JK flip-flop does. Hey, I'm assigning. Yeah, okay. And Eliza's coming at 3:30. So.
3:30?
Yeah. So I have JK and I have Q star. So 0, 0, 0, 1, 1, 0, 1, 1. And for with JK, if they are both 0, you have no change. And I never remember with a JK flip-flop which one is set and which one is reset. Can y'all tell me? When K is 1, that's a reset. Okay, so this one is a reset. Okay, and when J is 1, that's a set, and when they are both 1, that is a toggle. Okay, so this may not help me get my characteristic equation, and so we will do this. I did this in an earlier SI, but I'm going to show you a way that you can do it here too. So I'm going to add a column to my table here, and I make sure I have 8 rows. So J, K, Q, and Q star. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Okay, so wherever I had a Q for my output over here, on this table, I'm just going to copy what Q is. So here, when J and K are 0, both 0, Q star is going to be whatever Q is. So it just repeats what Q is. When J is 0 and K is 1, Q star is 0. When J is 1 and K is 0, Q star is 1. And when J and K are both 1, Q star, it toggles. So I'm putting the opposite of what Q is. So I just filled that in so that I have a nicer table that I can use. Okay, now let me get some more space. Hopefully, I don't know why this never works for me. Never works for me. Okay. Oh, but if I draw that nice long line, then, okay. All right, so now to get my characteristic equation, I'll make a Carnot map. And I'll put JK here and Q here. So 0, 0, 0, 1, 1, 0, 1, 1, and 0 and 1. And then, based on my truth table, see Q star is 1, when JK is 0 and Q is 1. JK is 0 and Q is 1. When J is 1 and K is 0. And when we have 1, 1, 0. Right there. Okay. That doesn't seem right. Because I set up my Carnot map wrong. Y'all didn't stop me. Okay. 1, 0, 1, 1, 0. Yeah. Is that right?
Yes.
I couldn't make that out. But yes, y'all think it's right?
Yeah, it looks correct.
Okay.
Yeah.
Okay, so I have that group, that. So this gets me that Q star equals, this top group is J Q prime plus the group that wraps around is K prime Q. And that does look like what I remember the characteristic equation for the JK flip-flop to look like. And it is. Okay, so now to write the code for this, I'm going to start module and then call it whatever I want, JKFF, and then my inputs, JKQ and clock, and then I'll have input J, K, and clock. Now when you actually start doing this on the basis board, you're going to have to do some more work to get your clock to work like a clock, but you'll have lots of fun to do with that. Now because this is a flip-flop, we want it to change on the clock's edge, which is why we have to use an always block. So because it's changing inside an always block, our output is going to be a reg. So output reg Q. Oh wait, well, okay. It does not matter what order you put these in up here, but I suddenly realized I had my output before all of my inputs, and I just didn't like that, so I'm going to change that. Okay, so now I want to have an always block, and that will be always at, and then I'm going to put positive edge clock for a positive edge trigger. If you wanted negative edge trigger, you put negative edge in there. And then I'm going to say that Q I would use a non-blocking assignment here, but he did not, so I won't. Okay, so Q equals J and not Q, or not K and Q, and end module. Okay, so now let's look at the characteristic, or the state table, state diagram. The state diagram is that what comes next. The characteristic. Oh, one must be based on the characteristic equation and the other on the characteristic table. Okay, so now let's do one. So not from the state diagram. Well, really, the state diagram and the characteristic table are the same. So let's look and see how we would do that from the characteristic table. So we have our characteristic table. So we had Can y'all remind me? It was 0 when k is 1. Yep. Okay. So if I want to write one based on this, then I'm going to do it similarly to how I did the multiplexer problem earlier today with, I had all these different examples. Da, da, da. Yeah. So I had all these different examples that I did. If you go back and look at the problem that I did with the multiplexer, I showed how to do it using just if and else if, and then how to do it using is, if, and else if, and vectored signals, and then how to do it with a case statement. I would always do it with a case statement because I like case statements. So on this one, I would do module JK, and then JKFF, and then JK clock Q, input JQ clock, output Q, and then again we'll have an always block. And in our always block, always at, and we want this to happen whenever J or K changes. What did I put on my always block last time? I don't remember.
Positive edge.
Positive edge. Right, right. So sorry, I guess I do want, do I want the clock on this one? No. No. I don't. I do want the clock on this one. I don't know why I didn't put that. I do want the clock. Yeah. Always at positive edge clock. Okay, so this is this is a good way to do this, and I'm going to show you, and you can use this in your other programs too. We're actually going to do 2 always blocks. So our 2 always blocks. One of them is going to set up what the next state is going to be, but the second always block is going to be what actually advances the state. So like on the one we just did, we did positive edge of the clock, so it didn't do anything until you got to the positive edge of the clock. But at the positive edge of the clock, it had a simple statement as to what the output was going to be. So here I am going to have 2 always blocks. So one will be always at JK. So this is whenever JK change. It's going to set it up to make the change for the next time there is a clock change. And then I'm going to have a case statement. And I want to look at both J and K, so I can put them in these curly brackets. So this treats JK as a 2-bit binary number. And then because I'm a little bit lazy and it takes longer to write 2 apostrophe B00 2 apostrophe B01, to write that, I'm going to write 0 colon 1 colon 2 colon and 3 colon, and that's our values over here. So this is 0 0 0 0 0 1 is 1 1 0 is 2 and 1 1 is 3. If I were really careful, I'd put a default in here, but I don't really need to because those are my only possibilities. So end case. And then case 0, then I'm going to have a new, this output needed to be a reg because I'm going to put it in an always block, and I'm going to have another output in this always block, and it's going to be my next Q, and it also has to be a reg. I'll just put, that's too messy. I'll put it as 2 lines here. So output reg Q, output reg next Q. Okay, so this always block is setting up what the next Q is going to be. So so when JK is 0, next Q equals Q. When JK equals 1, next Q equals 0. When JK equals 2, next Q equals 1. And when JK equals 3, next Q equals not Q. So now we're all set up. So if J and K change, we're ready. And then at the next edge of the clock, please no. I don't know what I'm doing wrong. If any of you are OneNote specialists and can tell me why I cannot get OneNote to add more space, and I can't. Sometimes I can just drag and it'll add space. No, it's not doing that. It just makes me feel stupid. It makes me feel my age. Okay, all right, now, okay, so pretend I'm continuing on below this. I will have another always block. So this will be always at, and this time it'll be at the edge of the clock. So I'll do always at, you could do positive edge or negative edge, positive edge, clock. And then all I'm going to do in here is say that at this point I want Q to equal next Q. And that's it. That's all that always block needs to do. And then we can end module. And you can use this same setup for all kinds of sequential circuits, and you'll be doing lots of them this semester. So you'll have one always block where you set up what you want to happen whenever the clock changes, and then you have another always block that actually makes that change. Okay, so that is actually, I only had time to do the JK flip-flop, but that I think gives you what you need to know on how to do this one, because I think we pretty much did everything you would need to know how to do. So are there any questions that you don't understand what you need to do with this one? Chat. Thank you. Oh, you're welcome. So anything else? Because if not, I'm going to sign off and save this and upload it for all to see. All right.
All right. Thank you. You have a
Okay.
good day.
You too. Bye-bye.